when we're using numeric integration, it's important to be able to think, is this answer going to be a little bit too high, a little bit too low, kind of right on average? And that can depend on the shape of the function. So let's look at some examples. Remember, the first example we drew was something like this. And we said, if you do a left method, you get that. If you do a right method, which would be the same as what we've been doing as an upper bound for a big whole interval, you would get that. That would be an upper bound. And we said if you did a guess, then you'd be halfway between the upper and lower end. And another way to see that is that if you take that purple line and rotate it, keeping it centered, keeping it going through that point, which is in the middle left to right and the middle up and down of that rectangle, you could see that then as, so we've got that, we've got the upper bound, and then you would get a line that does that, which is the trapezoid method. But let's compare that to the curve we had going through there. You can see that the guess is going to be a little bit lower. The area under the curve for the guess is going to be a little bit lower than the true area under the curve. So here the guess is less than the true area in this region. So what would it take to see the guess be higher than the area under the curve in that region? What kind of shape would it take? So that's the kind of question we're asking now. So in the homework, let me get you set up on this because the homework just describes a table, but I want to actually draw it out here. Let's say you have a table with 3 columns and 4 rows. And we'll say lower bound, upper bound, and guaranteed exact. And then we'll have like that. And this column will be, this row will be for the left method. This will be for the right side method. This will be trapezoid. And this will be midpoint. And remember, the midpoint here is horizontal. Does it make sense that we could call trapezoid the vertical midpoint method? Because trapezoid is drawing this slanted curve, or this slanted line, which has the same area under it as this guess, which we've been drawing, which is the midpoint vertically. So I'm not going to say that trapezoid should be called the vertical midpoint method, but it's good to think about how midpoint horizontal, the midpoint method takes the horizontal midpoint and then determines the height of the box based on that. And trapezoid is kind of using the 2x values you already have, getting y values, and then taking the vertical midpoint of those. So in these boxes, we want to draw shapes that show when left is a lower bound, when left is an upper bound, and when the left method is guaranteed to give exact answers. In this case here, you would probably agree that left gives us a lower bound, right? So I could draw a curve like that and draw a left side box, and that's showing us that left is giving me a lower bound there. What kind of function looks like that? How about root x? What else? Just how about a plain old line? Is left giving me a lower bound in that case? I think so. A plain old line with positive slope there. What else would give me a lower bound? What other shape of curve would left give me a lower bound for? How about something like e to the x? Something like that. And then I want to think, what do all these shapes have in common, and what does not seem to be important here? Can I say left is a lower bound when the function is concave up, like e to the x? Well, it's also a lower bound when the function is concave down. So concave up, concave down doesn't seem to matter. What is an important property of all three functions here? Take a sec to think about it. Hopefully you came up with the fact that all three of those are increasing. And concave up, concave down doesn't matter. So in the homework, you just have to say what the shared property is. You don't have to say what doesn't matter, but I just wanted to emphasize it here. So if left gives a lower bound when the function is increasing, you might reason by analogy. I love reasoning by analogy. It's like my favorite thing to do. But reasoning by analogy, what shapes would left give you an upper bound for? And then, again, reasoning by analogy, what shapes would the right side method give you a lower bound for? And what shapes would the right side method give you an upper bound for? And then for trapezoid, let's look back up at what we had here. We were using a trapezoid, and what box would you put this in? Well, trapezoid there is giving us a lower bound on the true area, and so that would go in this box. So again, I'd have a function like this and a trapezoid drawn underneath it. It doesn't really matter how far down it goes. So that's one example. Can you think of another example? Here, this is concave down and increasing. Can you think of another example where trapezoid would give you a lower bound that's not both concave down and increasing? Maybe still increasing, maybe still concave down. What kind of curve would trapezoid still give you a lower bound for? Pause the video and think it through. So hopefully you came up with a curve like this, which is concave down still, but decreasing. So the important part here seems to be concave down, but increasing or decreasing doesn't matter. And then midpoint is awful hard to think about. Let me give you an example and not categorize it. So if I had a shape like that and I wanted the box from here to there, I would take the midpoint horizontally of that box and then find that value on the curve and then draw my box height like that. So that's one way. One example you might use. And then what if I had a curve that was like this and I wanted that region? I would find the midpoint, find that height, and then draw a box like that. So that's two things that can get your thinking going. What if it's not purely one or the other? What if it's like this? This gets trickier. If I'm going from here to here, take the midpoint, and then is that an upper bound or a lower bound? And you have to start thinking about this little area here versus this area here that's included in the box but not included in the function, versus this area here that's included in the function but not included in the box. So thinking about examples like that will help you figure out the midpoint row. If someone asks me which is my favorite method here, trapezoid or midpoint, for example, it turns out midpoint is slightly more accurate for functions where you can use it, but it's really hard to do unequally spaced boxes with midpoint. So if you've got a data set with unequally spaced x values, you basically can't use midpoint unless you put a lot of extra thought into it, which is usually not worth it, but you can use trapezoid. So midpoint is in theory better for equally spaced data, but trapezoid is useful in so many more situations in applied work. I got to go with trapezoid.